Hey everybody, in this video we will talk more about melting and boiling point trends, and we will get more into specific ideas rather than generalized ideas. And for this first part we will talk about the trends for melting point, and this applies to covalent compounds. So of course we learned that stronger intermolecular forces results in higher melting points. But did you know that symmetry also causes higher melting points? And you can only use symmetry as a factor in determining how high the melting point is if the intermolecular forces are similar. So keep a note of that. And remember, intermolecular forces is always the dominant idea, while symmetry can be the secondary idea. And the reason why symmetry matters is because symmetrical molecules stack well into a crystalline lattice, while less symmetrical molecules don't. And if you're stacked more well in a crystalline lattice, you will have more order and thus more powerful bond strength. Now, let's talk about two compounds and let's compare their melting points. So they both have the same molar mass because their molecular formula is C4H10O, and these are both isomers, and they're isomers because they have the same molecular formula, but they are shaped differently. So these are isomers, and notice how this one is kind of like a long chain, while this one is more so branched. And let's compare their melting points. So if you notice, both of these compounds have an OH, which means that both of them have hydrogen bonding, and both of them have similar LDFs, but not exact, as you'll see later. And this is because they both have the same molar mass, which is a trend that applies to the strength of the LDF forces, because higher molar mass correlates but does not explain the higher LDF forces. So we can use LDF, we can't use H bonding. What about dipole-dipole? Well, both of these compounds have dipole-dipole, and they're about the same, since the only polar bond is the OH bond, and all you'll get is this bond dipole and possibly this bond dipole, and this happens for both of the compounds, so this is unreliable to compare the two. So we can't use any of the three LDFs because they're pretty similar, so we can move on to symmetry. So which molecule looks to be more symmetrical? Well, I think that this molecule is more symmetrical because if we pretend that all of these are just, balls, and we could draw a CH3 as a ball, and the C as a ball, the CH3 as a ball, an OH as a ball, and a CH3 as a ball, we can see that there's a lot of symmetry going on. There's symmetry over here because when you draw a line of symmetry, the two sides look exactly the same. There's also a line of symmetry over here, and over here. So as you can see, this molecule has a lot of lines of symmetry. Now let's look at this molecule. Let's draw it just like how the picture states it. So just like that, and we can consider an OH as a ball as well, and it kind of looks like that. So are there any lines of symmetry? Well, yeah, there are quite a few over here. And if you imagine that you were looking at this molecule from above, you'd notice that you could cut this in half from above. And we could also think of this in terms of planes of symmetry, which is in the 3D world, and these molecules are 3D, so it's more appropriate to use planes. But lines are simpler, but we'll use a plane here to show that these molecules can be cut in half from above. So we have two lines or planes of symmetry, and there aren't really any more. So because of that, the second isomer will have a higher melting point because it is more symmetrical. So if we compare their melting points, we can see that this has a melting point of 25C, and this has a melting point of negative 89.8C. Now let's talk about boiling point trends for covalent compounds. We know that, of course, the stronger the intermolecular forces, the higher the boiling points. But what if the LDFs are similar? If they are similar, then the surface area of molecules will result in a higher LDF force, which results in a higher boiling point, because for a higher surface area, there are more surfaces on which positive/negative partial charges can form. So we know that these two molecules have similar IMFs, or intermolecular forces, so we have to compare them by looking at their surface area. So surface area, how do we really think about that? Well, in general, things that are straight-chained will have a higher surface area, and those that are branched or more compact will have a lower surface area, because things that are more compact will have a lower surface area and volume, of course. So we could also think of this by drawing it. So for the chain that we see for our first isomer, we can see that it might look like this. So 1, 2, 3, 4, 5. It has this much surface area, and surface area is just the area that's on the surface of the electron cloud. Now, what about this branch chain? Well, this branch chain kind of looks like this, right? And let's draw the electron cloud for that. And notice how the surface area on this is higher than the surface area on this, since this is more compact. And because of that, this means that our first isomer, isomer 1, will have stronger LDF forces since it has a higher surface area, and this results in its higher boiling point. So as you can see, isomer 1 has a boiling point of 117.7 degrees Celsius, while the branched one has a boiling point of 82 degrees Celsius. So notice that for boiling point, the surface area and the LDF matters more, while for the melting point, the symmetry matters more. And that's just because the solid to liquid transformation involves breaking a crystal lattice. So this crystal lattice is very important, and because of that, symmetry is more important. Meanwhile, for liquids turning into gases, the crystalline structure is not there anymore, so the symmetry matters less and the LDF matters more. So now that we're done talking about these special trends that occur, let's now look at some practice questions in order to test how well you can order boiling points and melting points based on your knowledge of inter- and intramolecular forces from this video and the previous video. So we are going to order HF, HCl, HBr, and HI, and this might be a little bit difficult. So let's make a chart, and we know that these are going to be covalent compounds, so they will either have LDF, dipole-dipole, or hydrogen bonding. So we make a chart, and we see that HF is the only compound that can form hydrogen bonds, since HF is one of the types of bonds that can form hydrogen bonds. So immediately, we know right from the start that HF will have probably all three of these forces while the rest of them won't. So this one will have the highest boiling point. So this is number 1 on the chart for now. Now, what about the other three? So we can ignore HF right now because we know that that has the highest boiling point since it has the most intermolecular forces, and hydrogen bonding is especially powerful, so that just makes it, have a super large boiling point. Now, what about HCl, HBr, and HI? How do we distinguish between the three? We know that they all have LDF and dipole-dipole, so we can, order these in terms of the strength. So we know that Cl is the most electronegative atom, so that means that the dipole-dipole forces on HCl will be the highest, or the second highest if you include HF. And then next comes HBr, and next comes HI. Now, what about ranking these three in terms of LDF? Well, we know that the bigger the molecule is, or the more electrons it has, the stronger the LDF. So HI wins, HBr gets second, HCl gets third. Now, the next question we have to ask is, do we consider the dipole-dipole forces or the LDFs as the more important factor? So in order for us to distinguish between which force matters more, we have to think about how close these forces are relative to each other. So in this case, we will ignore the dipole-dipole rankings since the electronegativities of Cl, Br, and I are very similar. You notice that they are 0.2 part, 0.3 part, and because the electronegativity differences are so similar, that essentially the dipole-dipole forces on these three molecules are very, very close or very similar. So because of that, we can not consider dipole-dipole as the determining factor for which one has a higher boiling point. And now we have to look at LDF. And the reason why we look at LDF instead is because the number of electrons differ by a lot. And when it differs a lot, that means LDF can differ a lot. And if you remember, I2 is a solid because it has so much LDF. And this means that LDF can be considered as a factor in considering which one has the highest boiling point. And in this case, we could do it since HCl has 18 electrons, HBr has twice as many electrons, and HI has, well, 18 more electrons. So notice that gigantic jump in electrons, and because of that, LDF will be very different between these three, and because they are very different, we can use that as a factor to determine which one will have the higher boiling point. So according to this chart, HI will have the second highest boiling point, HBr will have the third highest boiling point, and HCl will have the lowest boiling point. So I ordered everything, and HI is second, HBr is third, and HCl is fourth. So we just determined the order of the boiling points of these four compounds. So it was kind of hard because we had to think about whether the dipole-dipoles were similar or if they were different enough for us to compare. So when you compare boiling points, you sometimes really have to think about what's going on and whether things are worthy of being compared. So let's move on to another question. Let's compare the boiling points of cesium fluoride and sodium fluoride. Now, if we draw this out, we can clearly see that cesium is a larger cation than sodium because cesium is in a higher group than sodium is. And because cesium is larger, you'll notice that the ionic bond will be longer than the ionic bond between sodium and fluoride. And because longer bonds means weaker bonds, then that means that this will have the weaker bond, while the shorter bond will have the stronger bond, because if the distance between the two ions decrease, the attractions increase, and this is Coulomb's law once again. So I did not consider the charges as a contributing factor to which one would have a higher boiling point, since both of them have a +1 and -1 charge. So you can't really compare them if they're both the same, right? So therefore, in the end, I concluded that sodium fluoride had the stronger bond, so it has a higher boiling point. So sodium fluoride has a higher boiling point than cesium fluoride. Now let's move on to our next question. We have to compare sodium and iron. Now I know that the answer is basically there, but let's talk through this. Sodium and iron are two metals, and we have to think about metallic bonding. Metallic bonding includes both the metallic radius, which, obviously iron will have a larger metallic radii since it is a larger atom after all. But we also have to consider the electrons, and sodium has one valence electron, the 2s1. Meanwhile, iron is a transition metal. It has both the 4s2 valence electrons and the 3d6 valence electrons. So notice that there are 8 times as many electrons. So you have to consider these things when you're thinking about it. If the magnitude between the two is so different, then that factor must be the contributing factor to determining which one has a higher melting point. So let's read my nice explanation that I wrote out in green pen. Iron is bigger than sodium, and because it is bigger, you might assume that iron will have weaker metallic bonding since, a larger radius means less attraction according to Coulomb's law. But iron has 8 times as many electrons as sodium, and because of this, sodium has the strongest metallic bonds. and therefore iron will have a larger melting point than sodium. So you got to think about many factors when you compare two metals. It's not just about their radii, it's also about the number of electrons in this case, because we are talking about metallic bonds. So keep a note of these in mind, and remember, since this has 8 times as many valence electrons, think about what 8 times means. It means 8 times as strong. Well, I don't know about that, but it means a lot stronger. And even though you might say, oh, well, iron might be 3 times as large in terms of radius, you're forgetting that there are 8 times as many electrons for iron. And honestly, for metallic bonds, the number of valence electrons matters more than the difference in atomic radii. So metallic bonding has to do with a sea of electrons, so therefore the valence electrons is kind of a very important factor in determining the bond strength over the atomic radii. So let's now do one last question. We have to compare CCl4 and CHCl3. Which one has a higher melting point? Well, we have to compare the 3 types of forces that these molecular substances have. So both of these will have LDF, but one of these will have dipole-dipole. And this is because CCl4 is nonpolar, since these bond dipoles all cancel out and there's no net dipole, so it's nonpolar. But CHCl3, if you notice, there are 3 bond dipoles and they all point kind of downwards, and in the end your net dipole is a downward arrow, and because of that CHCl3 is polar and has a net dipole. Now both of these don't have H bonds, so we don't have to worry about that. So based on this information, we see that CHCl3 has 2 intermolecular forces while CCl4 has 1 intermolecular force. And when we compare intermolecular forces, we want to first consider the one that matters more, and in this case, the one that matters more will be the stronger bond, and in this case, it will be the dipole-dipole forces. And because CHCl3 has dipole-dipole while CCl4 lacks it, then without even looking at the LDF, we can kind of conclude that CHCl3 has a higher melting point than CCl4. Now, let's just say that we did look at the LDF. If we look at the LDF, we notice that they have a similar molar mass, although this one might have more electrons or a higher molar mass than this one. But regardless, they're pretty similar, and things that are similar are not very good for comparison unless they are the sole source of comparison. But in this case, it's not the only source of comparison. We could also compare these two compounds by their dipole-dipole forces, and since one lacks it and one has it, that's a more meaningful and more impactful way of comparing them, since the dipole-dipole forces matter more typically than the LDFs since it's stronger, and because of that, CHCl3 has a higher melting point than CCl4. Now this goes back to the idea of the HF, HCl, HBr, and HI. Notice how we considered H bonds first because those were the more impactful bonds, and immediately from that we kind of concluded that HF had the highest boiling point. And when we went to the other 3 compounds, notice that we skipped the dipole-dipole forces because these were too similar for comparison, and because of that we had to resort to another way of comparison, and this turned out to be the LDFs, which turned out to be pretty different. So that was a viable source of comparison, and that's how we reached our answer. So it does take a little bit of practice to get used to this, but with enough practice you will get the hang of it. So that's all for this video. Have a wonderful day!